All right, so here we have the chat. Hello, Gilbert. Hello, Vivian. Yes, we are here. Hello from Virginia, says Joel. Hello to Arvind, to Nijin. From Germany, Colombia. So we have a very international audience today also. All right, so yeah, welcome everybody. And yeah, let's get started. I hope that you are going to enjoy today's class. So in case that there is somebody new to these open classes, I am seeing some names that are not familiar to me. So maybe we have some people here who is new to open classes. So let me tell you that these open classes always are very practice oriented. Okay, so this is not a class where you are supposed to be there just listening and watching to what I am explaining or to what I am doing, but this should be an interactive class where you practice and you do the things while we are doing the class, okay? So in order to be able to achieve this, the very first thing that you have to do is to get the project for today's class. What is a project? Well, a project is a self-contained ROS project, okay? Then in order to get this project, what you can do is to click on this button that you are going to find here right above the chat. It says fork and open the class project, okay? So everybody go ahead and click here. I'm going to click here also myself. There we go. And then this is going to bring you to the main project page, okay? You are going to see right now that I am redirected here to the main project page. Here at the right side, you are going to find the streaming panel so that you have here the video and also the chat, just in case that you want to write some questions, comments, whatever, okay? I'm going to minimize this for now so that I have some more space here for my project. And then after some seconds, you are going to see that your project is going to finish loading and you are going to be in the main project page, okay? So the very first thing that you are going to see is the notebook for today's class, which contains all the notes, explanations, sample codes for today's class. So everything you are going to find it there in the notebook project. Let's see, mine is almost finishing. Meanwhile, this finishes loading. Let me also tell you that you are also going to have a copy of this project, of the project for today's class. You are going to have a copy in your account for ever, basically. Yeah, so this copy is permanent. Then how you can go to this project? Very easy. Here in the main, the construct page, you can go to the My Projects section here in the left side menu. If you click in My Projects, here you are going to find all your projects. And you are going to see the last one, which is the project for today's class, okay? ROS Developers Open Class number 191, okay? So yeah, and this project, you are going to be able to revisit it next week, next month, whenever you want, okay? So let me go back to the, open here the class page so that I can have all the comments. So we can see some new people here like Nijin, Efren. Okay, so let me go back to the project page and there we go. So mine has finished loading and as you can see, what you are going to find, let me clear the log messages. What you are going to find here is the notebook. Okay, this is the notebook with the instructions, explanations, everything for today's class. Okay, so everything you are going to find it here. Also the sample codes, commands that we are going to be executing, etc., etc. All right. Now, the topic for today's class, as I was saying at the beginning, is going to be object detection with OpenCV for ROS 2. Okay, so for this class, we are going to continue working with our beloved BotBox, which has been with us during the last classes. Okay, so we are going to keep working with the BotBox because it includes a camera, and that is basically all we need in order to be able to perform object detection, right? So for the new ones, let me also introduce you to BotBox. Let me share here very quickly the video for BotBox. There we go. So yeah, for all the people who is new into the classes, let me explain you that this BotBox is a portable robotics lab designed by us, by the construct, to help you teach robotics and ROS. So with this BotBox lab, you will be able to deliver experience-based robotics classes with minimal preparation and maintenance, because everything is provided in this box. So BotBox includes all that you need to make your students learn and practice about programming robots. Like, for instance, a set of wheeled robots equipped with LiDAR, sensor, camera, even a gripper, and a small warehouse environment. Also a simulation of the whole system. A set of ROS2 projects already made to test your students in simulation and the real robots, and many more things. So BotBox makes robotics education more accessible, allowing teachers to deliver practical robotics classes without unnecessary complexity, like setting up all the environments, etc. You can make the students practice robot perception, robot navigation, object detection and grasping, behavior trees, path planning, and many, many more. And furthermore, you can use the provided projects which have been prepared by us, or even create your own by creating your own project, okay? Then finally, you are going to also find information, more detailed information about this BotBox in the project itself, okay? So let me share back again my computer screen. So here in the notebook at the top, you're going to find all the information also, and a link here in case that you want to learn more about this BotBox warehouse lab. Super interesting kit, educational kit. All right, so okay, so with the introductions being made, let's get to the main point. So what is object detection? Well, I think this is an easy question. Most of you probably already know what is object detection, but basically object detection is sorry. Object detection in robotics is a computer vision technique that deals with detecting instances of objects of a certain class. For instance, a class would be humans, cars, animals, all right? From digital images or videos. It also involves other techniques such as drawing bounding boxes, like you can see here in the image, of the detected objects and labeling them with their respective class. Yeah, this can be very clearly seen here in this image. And object detection is super, super important in robotics because it provides, it covers many fields such as perception. Yeah, it allows the robots to perceive and understand the environment that they are in. It also provides object tracking. So it allows a robot to detect an object and being able to track that object. For instance, detecting a human and tracking that human and, for instance, following that human along the house, along a warehouse, etc. It also helps in manipulation tasks by detecting and locating objects. Also, it is useful, for instance, in safety environments. Yeah, so object detection can help robots identify potential hazards, dangers, obstacles in their environment. Yeah, and it allows robots to do intelligent decision making. Yeah, so by recognizing and by being able to detect objects in their surroundings, robots can better understand what is the environment they are in and take decisions, intelligent decisions, based on that. Okay, so object detection is a crucial, super important, essential skill, I would say, in robotics. Yeah. So we are going to be learning and practicing. More important, practicing how to do this in in a robotic simulated environment, in this case. All right? So how do we actually detect objects? Okay, so object detection is a huge field. Yeah, there are many different techniques that allow a robot to detect objects, and it is, furthermore, it is a field where there are being constant improvements, especially now with the eruption of AI and so on. So yeah, it's a huge field, okay? Then we are just going to be checking a couple of examples of how to detect objects, one which is more traditional or classical, let's say, and another one which is more new, let's say, more updated, okay? So first of all, we have some traditional computer vision methods, yeah, the ones that I said I would call them as the classical object detection algorithms or techniques, which involve extracting handcrafted features, for example, edges, corners, textures, from the images, and using techniques like sliding window and classifier cascades to detect objects. For instance, as you can see here in the example, you can detect rectangles in an image and base it on that, classify that image, and base it on some other techniques. For instance, based on a classifier trained with machine learning, you can tell that a certain image is very likely to be a face. Okay? We have some other methods like region proposal methods, single stage detectors. This is so. At the first part of the class, we are going to start with a traditional computer vision method based on a rectangle features. Okay, we will be doing it in a moment, and in the second part of the class, we are going to be using a single stage detector method. Yeah, so these methods perform object localization and classification in a single step, making predictions directly from the input image, okay? So in this first example, there are several stages, yeah, where we process or analyze the image, let's say. Here, the detection is made in a single step, okay? Then popular architectures include YOLO, which is the one that we are going to be using for today's class, which are the acronym of You Only Look Once, SSD, RetinaNet, and more, okay? This one is based in neural networks, okay? So we are going to be seeing an example of a more traditional computer vision method and a single stage detector method, okay? There are many more. As I was explaining a moment ago, object detection is a huge topic in perception. So yeah, we are going to just be having a quick look and overview at a couple of examples of how to do object detection, all right? And there are many more, okay? You can have a read, and there are many techniques, okay? Now, let's just start with the practice, because as I was saying at the beginning of the class, these open classes are meant to be very practice-focused. So let's already start doing some work, okay? So the very first thing that we are going to do is to start our simulation. Yeah, so we are going to start a simulation so that we can emulate a real scenario, all right? So for this, what you have to do is to execute the following command that you have here in the notebook in the launch the simulation section, yeah? So in order to execute this command, what we need is a shell, a terminal. So let's open a terminal by clicking on the following icon that you have also here in the notebook, and you are going to find this icon here in the bottom section of the project. Yeah, here you're going to find many different icons, but the first one that you can see here, this is the one to be used in order to open a new terminal. So I'm going to click here myself, and as you can see, this opens a blank new terminal. This is just a regular Linux terminal where you can type commands, okay? So in this case, the command that we want to execute is the following one here. So you can directly come here to the notebook, copy the command, and paste it into the terminal. And this is going to start all the processes in order to bring up the gazebo simulation. In this case, there you go. So after some seconds, you are going to see the gazebo window popping up here. You can make it bigger. Okay. In some cases, the gazebo client might start bugged, okay? I can tell that because, for instance, I cannot move the camera around. Right now, I am trying to move the camera around to zoom, but it is not working. Also, I can see here that I don't have any numbers in the real-time factor, etc. So if this is the case, don't worry. What we are going to do is to restart the simulation, okay? Then, in order to restart the simulation, you can press Ctrl-C here in the terminal to stop the command. There you go. And now we are going to go inside the simulation workspace here. Okay, CD simulation workspace. And here you are going to find an SH script which is named kill_gz. This script is for killing the gazebo simulation, yeah? So you can execute it here. Let me execute it like this, kill, not like this. I need to change here my keyboard, there we go. Kill gz.sh. I execute this script and you're going to see how the simulation is killed. And now all you have to do is to just execute again the simulation command, okay? And now it should open correctly. There you go, okay? You can see now that the camera has another point of view, and now also I can zoom in into the simulation, etc. Okay? Also, just to make sure that your simulation is working properly, what you can do is to try to move the robot around, okay? Then for this, we are going to open a second terminal here, okay? By using this button, you can open as many terminals as you want, okay? Then we are going to leave this first one here running, because here is where the simulation is running. In fact, we can rename this terminal so that we know that here we have the simulation. And here we are going to run a command in order to control the robot using the keyboard, okay? You are going to find, of course, this command also here in the notebook. If you go down a little bit, here you are going to find the command in order to be able to control, to command the robot, to move the robot using the keyboard, yeah? So I'm going to copy also this command and execute it here in the second terminal, which I'm going to rename to teleop, okay? So here I can execute this command, and then this is a ROS2 program that allows you to send velocities to the robot by using the keyboard, okay? Yeah, so here you have the specified keys. For instance, if you press into the I key in your keyboard, you are going to move the robot forward. If you press into the comma key, you are going to move the robot backward. The J key is going to rotate to the left. The L key is going to rotate to the right, and the K key is going to stop the robot, yeah? So let me do a quick test here and verify that I can move the robot. There you go. As you can see in the simulation, my robot is moving here forward, okay? Now I'm going to move it forward, backwards a little bit, okay? Yeah? So this is just to make sure that you can control the robot and that the simulation is working correctly, yeah? So far, so good, guys. Have you been able to load the simulation correctly? Yes, no? Tisas says that it's working. Also Gilbert, Harry Dude. Arwinder says, having some errors. What errors are you having, Arwinder? Okay, I can see, however, that most people has the simulation running. I still don't see my robot. Okay, try, if you're getting some problems or whatever, try restarting the simulation, as I did, okay? Sometimes the first time that you launch it, there might be some errors, but try restarting the simulation, as I explained it, okay? This is not an error, Arwinder. This is not an error. I also have this here. I should also have somewhere around here. See? So maybe you think that these red messages are errors, but they are not errors, okay? And in case that you are having something strange, just restart the simulation, okay? All right, then working now, says Arwin there. Okay, excellent. It's working. Okay, excellent. Then let's keep moving forward. Okay, so now that we have our simulation, let's define the mission of our class. Yeah, what is the goal for today's class? So if you have a look at the environment, you're going to see some objects here. For instance, we have a tree right here. Also, here in the right side, we have a person. Yeah. Also, around here, this is harder to see, but we have also a stop sign right here. Okay. So we have some random objects here in the environment. Then our goal for today's class is that our robot, our BotBox robot, is able to detect these objects. Okay, this is going to be our goal. Then let's start. For achieving this goal, let's start by creating a new ROS2 package where we are going to be placing the code for object detection. Okay, so the very first thing to do is to create a new ROS2 package. And in order to do this, you have the commands here. So let's open the third terminal, okay? So you should have three terminals, one for the simulation, another one for the teleoperation node. We can stop it now if you want. Meanwhile, we are not moving the robot. And a third one for creating here our package, okay? So let's go and copy the commands again. First of all, we go to the src folder of our ROS2 workspace, and then we copy the second command here, which is the one for actually creating the package, okay? ROS2 package create. The name of our package is going to be object detection, and here we are specifying some dependencies for our package. Okay, actually this is RCL. Okay, there we go. Okay, here, this is RCL Pi, okay, with only one L. I think it doesn't really matter if you have it wrong, I believe, but well, in any case, you can fix it here. Okay, so now we have created a new ROS2 package here, named object detection. Okay, so inside this package is where we are going to be placing our program for object detection. Yeah. So at this point, what we should do is to open the code editor, which is this second icon that you have here at the right side of the terminal icon. Yeah. Here, which says code editor. You can click here, and this is going to open a graphical code editor, which we can use in order to have easy access to all the folders, files that are contained inside this project. Yeah. So in this case, we have created our package inside the ROS2 workspace. So if you go inside here and inside the source folder, here you are going to find your object detection package. All right? Then, let's start right now by creating a first version of our object detection program. Yeah? So, we are going to create a Python script named object_detection.py. Where? Well, we are going to create it here, inside this object detection folder. Yeah? You are going to, inside the object detection package, you are going to find a folder which has the same name, object_detection, which already contains this init Python file here. Now, if you right-click in this folder, you can create a new file very easily, okay? And then here you can just enter the name of the file, which is going to be object_detection.py. And as you can see, this is going to create a new Python file here, which is empty right now, yeah, because we have just created the file. So, next step is going to be to paste some code into our Python program, right? And the code that we have to paste is this one. So let's select this code, copy it, and then paste it here into the code editor. Yeah? So you should have something like this, okay? All right, and then now, second step is to edit the setup.py file. This setup.py file, you are going to find it inside the object detection package here at the bottom, setup_py, okay? So this one, we are going to remove it, and we are going to copy and paste the one that we have here in the notebook, yeah? So copy and paste. What are we doing here? Well, basically here what we are doing is that we are creating an executable file from our Python script object detection, okay? So that we can run it directly from ROS, okay? And basically that's it, okay? So now the next step would be to compile and execute our program. But before that, let's have a very quick look at the code that we have here, okay? This is the same initial code that we used in previous classes, so some of you probably already know this code and are familiar with this code, but for the newcomers to the class, let's explain it very quickly. So what we are doing here is that we are creating a Python class, ImageSubscriber, and we are creating a subscriber here to this topic, camera image raw. This is the topic where our robot is publishing the data captured by the camera, okay? Yeah, so all the data that the camera of the BotBox robot is capturing is being published into this topic here, right? And then what we are doing is to create a subscriber to this topic so that we have access to this data, right? And this subscriber, of course, has a callback function associated, named listener callback, which is defined down here, and that we are going to check in a moment. And also important here, we are initializing the CB bridge, okay? The CB bridge is the class that is going to allow us to use OpenCV, yeah? Then, inside our callback, what we are doing is to, using our CB bridge, we are converting the images captured by the robot's camera, we are converting these images to CB2 format, yeah? So initially they are in ROS format and we need to convert them to CB2 format so that we can process them and analyze them properly through OpenCV, okay? And then finally here, we use the emShow method from CB2 in order to display the data captured by the camera. Okay? So basically, what we have here is a subscriber to the camera topic, and then using CV2, we display the images captured by the camera. Okay? Very simple initial code. Then, in order to test it, let's compile it. So let me select again the commands here from the notebook in order to compile our new package, object detection package. There we go. And then after compiling, we source our workspace and we execute our program with the following command: ROS to run, object detection node. Yeah? So we are executing the program that we have written here. Then let's execute it by pressing enter. And then after some seconds, we should basically see the output of this line, yeah? Which is the camera feed. So let's wait a few seconds, and there we go. We are going to see automatically popping up here the graphical tools, and here we can see the camera feed. Yeah. So this is what the robot's camera is capturing right now, live. Okay. For instance, if we move a little bit the robot, we are going to see how the camera feed changes. Let me move the robot a bit forward, for instance. There we go. And if I move back to the camera feed, you're going to see how the camera feed is updated. Okay? Now, what we are going to do is to move the robot around the warehouse to put it to, we are going to move it to the stop signal, which is here. Okay? So let me move the robot a little bit so that I can send it. Be careful, okay, while moving the robot, so that you don't crash it against the walls and everything. Let me move here to the right. There we go. Rotate. Now move forward. Okay, and here more or less, I am already facing the stop signal. Let me rotate a little bit to the left, and here, if I check again the camera view, I can see here in the front already the stop signal. Okay? So, everybody, let's move the robot and put it here in front of the stop signal. Because now, what we are going to do, the next step, is to try to do the detection of this stop signal. Okay? Yeah? So, slowly and carefully, command your robot using the teleop program so that you have the stop signal here in the camera feed. Okay? Yeah? Yeah, okay. Arwinder also has spotted the error that I mentioned with the RCL Pi. Yeah, so far so good. Are you following? Have you been able to execute properly this first program? Water. Yes. Yes, Vivian is asking how you did it right and left. Very easy. Right is the L key and left is the J key, okay? So if I press to the J key, the robot is going to rotate to the left. You are going to see it, see? To stop it, it's the K key, okay? If you press the L key, the robot is going to rotate to the right until you press the K key to stop it, okay? So this is how I am rotating it, all right? Okay, Now, let's keep going. Okay, so what we are going to do now is to use one of the methods that we introduced at the beginning, which I introduced it as one of the traditional object detection methods. Yeah. So for this, we are going to use the Haar feature-based cascade classifier. Okay. So this is an object detection, a well-known in the field object detection algorithm that uses machine learning to identify objects such as faces in digital images. Okay. It works by extracting Haar features, which are simple rectangular features, as you can see in these images here. Yeah? These rectangular features capture the intensity differences between adjacent regions in an image. Okay? And then these features are evaluated using a boosted cascade of weak classifiers, where each stage of the cascade is trained with machine learning to eliminate non-object regions quickly, while preserving potential object regions for further processing. Okay? Well, if you want to get more, I don't want to get too much into details of all this, okay? But in case that you are interested, you have a link here to see more details of how this cascade classifier method works. Okay? Yeah? Now, what we are going to do is to implement this into our program in order to detect this stop signal that we have here. Okay? So in this documentation, there is a sample code that you can see here, which shows you how to detect basically faces and eyes. Okay? This is explained here in the basic example on how to detect faces and eyes. Okay? What we are going to do is to modify this code in order to detect the stop signal instead of the faces and eyes, like in this example. Okay? Then how to do this? Okay, for this we are going to have a look at the most important parts of this example code, yeah? Which basically is here. First of all, one key step is to load the cascade classifier, okay? So in the example code, we have these two lines, face cascade, eyes cascade, and CV cascade classifier, yeah? These lines, what are doing is to load the cascade classifier to be able to classify the object detected into a specific class. Yeah, for instance, a face, faces, or eyes. So we are going to change this to instead classify the objects to detect if they are stop sign or not. Okay? How we do this? By loading a specific classifier, which you can find here. Okay? Here we are loading a specific classifier that is going to allow us to detect, stop signs. Okay? This stop data, you can find it here in case that you are curious. Okay? Here in the code editor, you are going to find it down here. Okay? Stop underscore data XML. Okay? This is the classifier for the stop sign. Okay? And here you can load different classifiers depending on what object you want to classify or to detect. Okay? In this case, we want to detect the stop sign, so we load this classifier. Yeah? So this line, very important. Next is to be able to detect the stop sign in the image. Yeah? So for this, we use the detect multi-scale method. Okay? So we need to change also this line to call it from our stop sign cascade instead of the face cascade. Yeah? And then this is going to store the detections here in the stop signs variable. Sorry. Then, once we have the detections in the stop signs variable, what we are going to do is to iterate over the detections and then draw a rectangle as a bounding box. Yeah? So in the example code, we iterate over the faces and then we draw an ellipse. Okay? Now we are going to iterate over the stop signs and we are going to draw a rectangle where the detection is made as a bounding box. Okay? So, applying all this, the final resulting code is going to be this one. Okay? So, what we are going to do is to copy the code here from the notebook, the final code. Let's copy it and paste it here into our object detection Python script. So we can delete the previous version and paste the new one, okay? And here we can see again all the steps, yeah? So we have our class, we have the camera subscriber right here, we are initiating the CV bridge. Here is where we are loading the stop sign data classifier so that we are able to detect the stop signs in the image. And then in our callback here, we have to convert the image from ROS format to CV2 format. And we do a second conversion, which is convert the image from color to gray. Okay, so we convert the image to grayscale. Grayscale would be something like this, where the image only has gray colors, okay? Because the color data, in this case, it's not important, okay? Then once we have the image in grayscale format, what we do is to call the detect multi-scale method in order to do the detections and save them here in the stop signs variable, as we were saying a moment ago. And then once we have the detections, we iterate over the detections using a for loop, and we draw the bounding boxes, which are going to be rectangles. Okay? And then finally, we call the emShow method, which is the same as before, in order to show the camera feed. Okay? To display the final result with the camera image and the detection, the bounding box of the detections. Okay? All right, very well. So we have the code. Then let's test it. Okay? So next step is going to be to, again, we have to rebuild our package because we have changed the Python script. So let's come here and stop the program. Rebuild it. Okay, we need to build again our package so that we compile the new code, the new updated code. And once it is compiled, we source the workspace and we run our program again. There we go. Okay, so now let's go to the graphical tools to see what is the final result. And the final result is going to be something like this. Okay, so as you can see, our program now is able to detect the stop sign, and we are drawing a bounding box, which is a rectangle here, around the stop sign detection. Okay? You are going to see that depending on how you move the robot, how you locate the robot, the detection might be lost, you might get some errors, etc. Okay? You can play around, you can test a little bit and see how moving the robot, seeing the image from the different perspectives, etc., changes the output, the final result. Okay? As you can see here, I am losing the detection at some moments. Okay? All right. Let's go to the next step. So now we are doing the detection of the stop sign by using this traditional method more specifically the Haar cascade classifier method, okay? So now we are going to see how to detect people. Now, for detecting people, we are going to change to another method, which is the single stage detector, okay? Which also we introduced at the beginning of the class, okay? Here we have it, the single stage detector, okay? And we are going to use the YOLO method, you only look once method. Then this YOLO method, okay, so let's scroll down. Well, before moving to this, have you been able to do the stop sign detection? All of you, yes, no? Have you been able to do? Yes, Vivian says yes. Yes, the stop sign is detected, yes. Yes, yes, yes. Okay, excellent, excellent. Then we are ready to continue. Okay, then yeah. So this Haar feature-based method that we have just used has some downsides. Okay, for instance, rigid feature design. So the Haar features are manually designed and can only capture a limited set of visual patterns. They may not be effective in detecting objects with more complex appearances or under varying light conditions. Yeah? So if we have bad light conditions in the environment, we might have some problems doing the detection, and we might lose the detection. As you can see, it's happening sometimes here. Okay? It has other downsides, like it is a very slow training process, okay? Lack of generalization, so the trained classifier is specific to the object it was trained on and may not generalize well to other object classes or variations of the same object class, yeah? So this classifier is looking for a very specific stop sign. Now, in the case of a stop sign, there are not much variations of how a stop sign is going to look, yeah? But for something more complex, like for instance, I don't know, a dog, yeah, which can be very different from one class of dog to another class of dog, yeah? Then for objects which have more complex variations, then also these methods are not so effective, okay? So basically these traditional methods have some downsides, okay? Then we are going to switch to a different approach, which is the single stage method, and we are going to use the YOLO algorithm, okay? The YOLO algorithm is a very popular one-staged object detection algorithm that has gained widespread adoption due to its speed and accuracy, okay? It's very speed, and it works very well. It's very accurate in general terms, okay? Then, as we also explained it before, unlike the traditional object detection methods that involve region proposal and classification steps, YOLO treats object detection as a regression problem, allowing it to make predictions with a single evaluation of the deep neural network. Very important, okay? Then, yeah, so here we have all the different steps that are needed in order to use the YOLO method. So first of all, we need to load the model. We need to get the layer names, also identify the output layers. These are the layers of the neural network, okay? We have to load the class labels. Then basically summarizing the steps that we need to do in order to be able to use the YOLO object detection method is to, first of all, load the YOLO model. Second, for each incoming image, process the image, run the YOLO model to detect object and process these detections. Okay? And finally, once we have the detections, we draw the bounding boxes. Okay? Here you have details of all the different parts of the code, etc. I'm not going to go over all these, okay? I'm going to go directly to the final version of the code, which I have here, and then we are going to have a look here at the code itself, okay? Then let's copy the final version of the complete code from the notebook. There we go. And paste it here into our code editor. So let's remove the previous version and paste the new version. Okay? Then at this point we can already we can already stop the previous program, and yeah, final step here is to do the compilation and testing. But before that, let's have a quick look at the code. Okay? Quick overview. So we have our Python class. We have our subscriber to the camera data, right? We are creating the instance of the CB bridge. And here is where we are loading the YOLO model. Yeah? As you can see, we are loading the weights and a configuration file. Okay? These files, you have them also here. We are loading them from here. Yeah? So we are loading the model and we are getting all the layers of the neural network. Okay? Now, here, also very important, we load the classes, which are defined in this file, coco.names. This one, you can open it if you want. I'm going to open it here, and here you are going to find a list of classes. All these classes are the things that our neural network, our YOLO model, is trained to detect, okay? So this model that we are loading here is trained to detect all these. So we have a person, actually tree, no. Tree is not trained to detect trees, okay? So it can detect persons, bicycles, cars, motorbike, aeroplanes, bus, train, truck, boat, etc., etc., etc. Okay? So all this is everything that our model can detect. Okay? Then, I am looking here for here it is. Okay, I was looking for the stop sign. Okay? Yeah? So we have the stop sign and we have the person. Okay? Let's go back to the program. Okay. Then in our callback, we have the following. So we are, this line is the same as in the previous versions of the program. So we are converting the image from ROS format to CB2 format. And then we have to convert, well, not convert, but we have to get the blobs from the image, okay? Blobs is a term used in object detection, okay? And the blob is what, so we have to extract the blobs from the image, and the blob is what we are going to feed, to set as the input of our network, neural network, okay? So this neural network accepts as input blobs, okay? Not the whole image. All right? Then, okay, so once we feed the blob to a neural network, we are going to get some outputs. Okay? We are going to get the output layers, and then we process the output layers for detections. Okay? So we iterate over the outputs, and we iterate over the detections. Okay? And then we evaluate the detections using this confidence value. Yeah? So you can think of this confidence value as a score, or as how confident is the neural network that this object it is detected correctly. Okay? So here we are saying that if it is more than 50% confident that the detection is correct, then we are going to accept it. Okay? Yeah? And then finally, here we are applying a non-max suppression method in order to remove overlapping bounding boxes. Yeah, these overlapping bounding boxes, you can understand it better here in this image. Yeah, so at some point we are going to get a result like this one with many bounding boxes. Okay, then we have to use some method, in this case the non-max suppression, in order to remove all the bounding boxes which we consider are not valid, are noise, are errors, okay? So that we have something clean at the end, like this, okay? Yeah? And then, finally, we are drawing the rectangle, the bounding box itself, and we are putting text, okay? So we are adding to the label, to the bounding box, we are adding the label, so what is the detection, and the confidence value. So how sure our model is that the detected object is correct, okay? Yeah? All right, so let's see this in action. Then let's one more time compile our program. So let's go down here, let's recompile our program. There we go. And let's source and run our program. And let's see what we get. Okay, let's open the graphical tools to see the results. There we go. Okay, and there we go. So now our YOLO model is able to very accurately, as you can see, the accuracy is much better than with the Haar's model, yeah? So the detection is super stable. Actually, you can see that the confidence here is 0.97, which is very high, yeah? And we can see also that the detected object is an stop sign, okay? So in some, okay, then let's now put to test also our algorithm with the person. So I'm going to move my robot a bit forward here, so that I can have in the view of the camera the person here in the room. So let me move forward here. Let's go forward. Let me stop here. Turn to the right now to face the person. Okay, I think that now I should have the person in the field of view. And there you go. So there we have the person which with a confidence of 1, which is 100% basically. Yeah. So our YOLO algorithm is also able to detect the person. Yeah. So we can see also how it is, how we are printing here the confidence value and the level of the detection. Okay. And also you can see how the accuracy is very good. Okay. And we are able to detect this, as I was saying previously, because these are classes which are the neural network is trained to detect. Yeah, persons and stop signs. And any of the classes that we have here, our YOLO model is going to be able to detect them. Okay. Now, in some cases, you might have some results like this. Okay, depending on what is the perspective that you have from the object and so on. Okay, maybe some of you are getting some duplications like this, okay? Don't worry. If you get results like this, there is a challenge here in order to solve it. So in case that you have some results like this, can somebody tell me what would you do here in the code in order to avoid these kind of situations? What would you do? Any ideas? So Mara says, I am detecting a fire hydrant as well. I don't know where you are detecting that. Change the threshold. Filter out low confidence results. Exactly. So one thing that we could do in order to avoid these kinds of situations is to increase here the confidence threshold. Yeah? Because here we are letting pass any detections which has a confidence higher than 50%. Yeah? So we could increase this in order to try to filter out this kind of situation. For instance, here we have a 51. So if we increase this to 0.9, this detection would be discarded, okay? And we would only have the 99% detection, okay? Yeah? And finally, I'm going to do, I'm going to move the robot in order to face it to the tree, okay? Let me move it so that I am facing the tree. I need to move in that direction. Let me move here. Okay, let's stop. Rotate a little bit. There we go. Okay, so now I should have the tree here. Okay, there we go. And as you can see, the tree is not being detected. Why is that? Because the tree, if you look for the word tree, this model is not trained to detect trees, okay? So this is going to be the homework that you are going to have for this class, okay? So using some of the methods that we have explained during today's class, okay? You can use, for instance, the Haar's method, you can use the YOLO or another one of your election. You have to be able to detect the tree here, okay? So this is the homework that I'm going to put to all of you for today's class, okay? Yeah? Is it clear? Is it clear the homework? The task that you guys have as homework? And as always, please, if you achieve to, hey, I am detecting a clock there with a 55%. Okay, I can understand why this could be mistaken by a clock, okay? The rounded shape and so on, okay. So this is interesting, yeah. So for instance, here, it has a 70% confidence. So if I increase the confidence value, I would filter out this detection, okay? Yeah? Yeah, Jose. No, you are not the only one. Everybody is going to have tree here, but this is because we added it during while preparing the class, okay? And we forgot to remove it, but it is not in the default classes. It is not tree, okay? So that is an error. All right, guys, then, yeah, so I'm going to leave it here. I hope that you enjoyed the class. I hope that you learned something new and that you get motivated by this. I encourage you to try to solve the task that we left you as homework and that you share your results with us in our social networks, as always. And yeah, I will see you in the next one. Thanks, everybody, for attending. And as always, until the next one, keep pushing your ROS learning. Bye-bye.